Hey folks, welcome to lecture 3.3. Today we're going to be talking about covalent compounds. So in the past couple days we've been looking at ionic compounds, and now we're moving on to covalent. And the difference between these two types of compounds will be in what kinds of bonds they form and what they do with electrons, and in the types of atoms that make these bonds and make these compounds. So here, let's take a look across the top, a little bit of a review, that ionic compounds form ionic bonds, and ionic bonds do what with electrons? Ionic bonds transfer electrons, right? Like a metal gives electrons to a nonmetal. Well, in a covalent compound, covalent bonds share electrons. So covalent, right? Like co is together, cooperating, coordinating, right? Covalent is together with valence electrons. So the valence electrons are shared between two atoms. That's how they fill their shell. So the core concept here right away is that covalent compounds are composed of molecules with two or more different atoms. A molecule is two or more atoms held together by covalent bonds, and the diatomic elements exist as molecules composed of two identical atoms. So more on that in a couple slides, but this includes a great variety of cellular compounds, proteins, carbohydrates, DNA, RNA. All of these are covalent compounds. They are all molecules held together by covalent bonds. So these molecules, two or more different types of atoms, but here looking at non-metal atoms. That is the key. Now recall that ionic compounds would be one metal and one nonmetal, right? One from the left side of the table, one from the right side of the table. Covalent compounds are all nonmetals. So the right side, upper right of the table. And these molecules, like we said, there can be a great variety. They can come in many different shapes, different sizes. It can be as small as just two atoms, or as large as thousands of atoms, like proteins that are composed of carbon, hydrogen, oxygen, nitrogen, sulfur atoms, right? In like almost an infinite variety of numbers and arrangements. So the smallest ones can simply be two atoms with a covalent bond between them. But the covalent bond is the key. So here's an example of a very simple molecule, H2, right? H2 means two hydrogen atoms with a bond. And this is how hydrogen is naturally found. It's actually as a molecule. Like H, an atom alone, is not how hydrogen exists naturally. It's called a diatomic, because di means two, and two atoms. So it's a diatomic element. And the reason will make sense when you think about the valence electrons. So one hydrogen atom has one valence electron, right? But the first row needs two electrons to be filled. So hydrogen wants another electron to be more stable. So instead of getting that electron from an atom as an ion, what it can do is find another hydrogen atom, also with one electron, and they can join together, and now they have two, and they can share those two electrons. So one way you'll see this drawn is like this, where the dots represent electrons, and we see that this hydrogen has two, and it's happy, it's complete. This hydrogen has two, and it's happy and complete. and those two are being shared. So back to the text here. Two hydrogen atoms join to form a molecule of H2, and the valence electrons are shared. Individual H atoms have a partially filled n equals 1 energy level with 1 electron, and the hydrogen molecule has 2 electrons and a filled n equals 1 energy level, right? So we can kind of see why these would be nonmetals then, because nonmetals are more likely to accept 1, 2, or 3 electrons than to give them away, like the metals are. So instead of fully taking 1, 2, or 3 electrons as an ion, it can share extra electrons with other atoms. So what is a covalent bond? The key concept here is that a single bond is just a type of bond formed when two atoms share 2 valence electrons. Typically, 1 electron contributed from each atom. So an example on a previous slide of a small covalent bond, molecule is HF, right? And if you remember that H has 1 electron, we could draw it like a dot like this. Fluorine is in group 7A, and it has 7 valence electrons. So sometimes you'll see this notation with dots, like a dot symbol. So you see seven dots around here for the 7 electrons. And we know now from ions that fluorine, you could say, wants 1 more electron, or needs 1 more for a complete shell. And hydrogen needs 1 more, and it only needs a total of 2. So if they move towards each other, we can see they can share like so, and we get an H, F, and here in the middle, hydrogen has 2, fluorine has 8, and the 2 electrons we can just turn into a single line indicating a bond. All right. So anytime you see a line like this between 2 atoms, that means 2 electrons. So the bond is 2 electrons. And this HF here is an example of a molecular formula. And the molecular formula, which again, it can be up to thousands of atoms in a molecule. We obviously will stick to more reasonable ones than that, but the molecular formula specifies to us the composition of the substance, the identity and amount of each element in the molecule of the substance. So we encountered this notation with subscripts before with ions, and they mean the same thing here, right? The subscripts tell us how many of that atom just prior to it there are. So here in this picture, right, we have H2O and H2O2. So they're both just hydrogen and oxygen, and that's it. But they're clearly not the same. H2O, more commonly known as water, and H2O2, more commonly known as hydrogen peroxide. So the H2O means there's 2 hydrogen atoms and 1 oxygen atom. H2O2 has 2 H atoms, but it has 2 oxygen atoms. Okay, and so it's going to be a very different molecule. It's going to be put together differently. The shape is going to be different, and like biologic effects are going to be different, right? So I'm going to show you another example molecular formula. So the number and arrangement of the atoms does matter, right? Like we saw, the difference between water and hydrogen peroxide is just a single oxygen. Here on the left is a quite a bit larger molecule, 24 atoms, right? C8H10N4O2. And so this is kind of called a ball and stick model, and we'll get to shape in the next section. Nothing quite this complicated, but you can see the black dots are carbon atoms, the white ones are hydrogen, the blue ones are nitrogen, and the red ones are oxygen. Okay, and this little molecule here, C8H10N4O2, is more commonly known as caffeine. I think I've seen this on a few mugs and shirts before. Great drug. It's a drug that I use every day. On the right, something that, it has all the same 4 atoms, different numbers, right? C17, H21, NO4. And you can see the arrangement here, right? It looks a little bit different. It's bigger. It's the same 4 things. This is not caffeine. This is cocaine. A very different kind of drug that we should never use, right? And so the number matters. The arrangement of the atoms matters. And this can all be drawn from the molecular formula. Okay, we'll leave it here. And on the next part, we will talk about naming covalent compounds.